Okay. Don't know if the audio's there yet. I'll know in a second. Aha. I know it's there. So, let's take a look at the homework. So, if we look at this problem, and he wants to know the I will tell you my computer is very slow today. I do not know why. All right. So step one in all of these is to figure out what the, okay, I don't know how things are going to go here. This is very odd. Okay. I have an AX, I have an AY, I have a BY. Now, the triangular load can be turned into something a little bit different. Let me show you. By going back to the problem and doing another grab. This time I'm going to grab the top or the bottom of it. I'm going to paste it right over here. I'm going to create an equivalent where this is 4. I'm just going to use the numbers 4. If you look at this area, that is the value of that load, where the right end is 4. So if I had a triangle that was 4 and then 6, the area of that triangle, 4 times 6 over 2, or 12. Since it is a triangle, its location is 2/3 from the light end. In other words, if I had a bunch of bricks stacked and the bricks were such that they were homogeneous, meaning each one weighed the same, and I stacked them like this, then the center of weight, if this was of length L, it would be L over 3 from the heavy end and 2L over 3 from the light end. That's where the centroid of this or center of gravity of this mass of bricks is. So in fact, since this is a value 6, this value is 2/3 of 6, or 4. I'm trying to find something to put under. Hang on. Yeah, I guess I'll just have to try to wing it here. So that'll be 4, and this will be 6 over 3, or 2. So in fact, you have this a distance of 2, and this, your distance is 4. If I want to know, well, first of all, I've got sum of the forces in the x equals 0. This doesn't produce a force in x, and nothing actually does produce a force in x, therefore there's nothing held here. So Ax equals 0 here. So I'm just going to take that off the drawing and list this as AY, list this as BY. And now I'm either going to choose B or A and B, but I'm going to sum the moments. I'll start with A. I'll start with that being positive, meaning that this moment goes in that direction, which is a minus 12 times its moment arm of 4. Then this one goes that direction. If you check this, that's positive, which is BY, and it's 6 and 6 are 12. So according to this, if you look real close, you end up with BY is equal to 4. You come back in, and now you can sum the moments about point B. You'll notice I always pick that. That's just a standard I always do for a sign, because of sign conventions in math. So now you're summing your moments about this point B here. So this is producing a negative moment, that is the minus AY times 12. It's still 12 to both ends of the beam. And this one is producing a positive, and it's 12. However, it's actually 6, and then add 2 to it, and you get this. So you'll find AY is equal to 8. Now the question you have is sum of the forces in the Y. Make that positive, equals to, I've got AY and BY going up, and minus 12. So in fact, this became a check. So I've got 8 on the left, and I've got 4 on the right. Now I'm going to do this. I'm going to go back to my picture yet again. Depends on which way you want to look at it. I'm going to do it both ways. So I'm going to grab the right end, drop it right there. I'm going to go back. I'm going to get the left end. I'm going to drop it right over here. Now I didn't put the distributed load on it because what I'm going to do, okay, so I'm going to go down this and say working from the left and working from the right independently. Okay, on the left, I will have a value of 12 right here, and it was 2 here and 4 here, and I'm going to have a value here. I believe it was 8, but I better check that. Yeah, it was 8. Now, the loads. It might be beneficial at this point to represent or draw your loads in such a way that they would be designated as positive. Here's what I mean by that. Hang on. I think I do have this up, but I have the wrong book, and I don't know if it's, wait a minute. Nope. Is it that one? Yes. So if we look, okay, give it a second. Can I erase? There is a pile of stuff on here, and they changed the way they did everything, so lucky me. Okay, so if you look at the sign conventions here, this is positive normal force. It's in tension. This is a positive moment. It basically creates, you could kind of think of it as creating a dip down in the beam. This one's the most unique. One way to remember it, there's many ways. One is to remember that this is the normal, if you're going to remember it in this sign convention. In other words, a positive normal mixed with a negative direction. In other words, this gives a positive. Okay, this is in the negative direction, negative x direction, positive y direction. So if you go back to our drawing, on the right side, the shear must go down if it's presented on the right. Now, what we're going to do is I'm going to do this on both drawings in a second. Now, I'm going to go over here, and I believe I had a value of 4 over here. Okay, let's put a positive drawing here. Here's my normal. I didn't continue to label this. And then my shear. So you'll notice if I compare the direction of each of these, it's equal and opposite. So that's the first thing to notice. Second thing to notice is the best thing to do is to assume and draw them in a positive direction and then work the problem. In this particular case, as time goes by and you move through other courses, it is best to leave these as negative and not go back and say switch the direction here. And you won't find that out in this course, but you will in the next. So, first thing to do is you've got 3 equations and 3 unknowns here. Sum of the forces in the x giving 0 tells you that this is equal to 0. If you do that over here, you get the same thing. Person over here would say, okay, now I need to sum the forces in the y equals 0, and what I get is an 8 minus 12 minus v. So move the v over, and you get minus 4. Okay, now let's go to this drawing, the one on the right here. We're going to sum the forces in the y equaling 0. We're going to make, now I did this, I should have, this is something I should do so that, you know, and he does this in the book where he basically designates a particular direction. Okay, sum the forces in the y, you get a 4, and you get a v. Turn around, you get a shear of minus 4. Now, here's what's so interesting. Opposite sides, same value here. That's because if this is in fact, if the v shear is going in this direction on that face, it has to be going on in that direction on that face for equilibrium. Okay, let's move on now. On the left drawing, sum of the moments equals 0, and the best thing to do is pick the point where the slice is. In this case, I think it is labeled as a C. Yeah, it was labeled as a C. Now, if you pick that point and you sum the moments here, you've got, and here, you got to designate what you consider to be positive. We will take this one first, and it is positive. Well, first let's take the moment here. It turns out to be positive, plus my 12 times my 2. So my 12 times my 2. And then this one, it is a minus 8 times a total of 6. So, excuse me. So what you end up with, okay, so I guess what I'm going to do is move these to the other side. I end up with 24, and I end up with a positive 24 because this happens to be 48, that happens to be 24. I moved that over, this became, the larger number became positive, and I end up with a 24. Now, let's do it on the right drawing. You don't have to do it on both, but if you want to check, you can do it on both. Sum of the moments, it's an ugly looking summation symbol. Sum of the moments equaling to 0 about the same C point. Equal to, now this time my moment is drawn this way and positive is this way. So turns out I get a minus. And it looks like I only get a force going this way. So it turns out that becomes 4 times 6, and the moment falls out to be 24 here with a positive. So as you can see, either way you look at it, either side, you should get the same value. Let's move to a more complex problem by going into the book and rolling down here and trying to find one that has a lot more complexity on it. Let's see. I'm looking for somebody that has... Yeah, we'll start. I'm trying to see what the difference between uh, 7, 9, and 7, 10 is. Okay. We're just going to do 7, 9. Let's see. Okay, so let's take a look at this. I'm going to slice it up again later. Okay, first I have to find the reactions against the fixed structure. Okay, that fixed structure is the wall. At this point, I could, if I want to be completely legitimate in so far as what they do in the book, here's what I would do. Let's go in, take the picture again, but only take that portion of it. Now this is being nitpicky, but I'll be that way for a short period. Okay, it wouldn't paste it. There we go. So I know that the wall, based on the structure here, look up here at the structure, I can tell you that the wall, and I'm just going to draw them this way. I'm going to assume a direction. I'm not basically going to say this is how they're going. I'll call this just tension. And in the problem statement, he stated that it was 8 was the load here. So this is just 8. So if I just come up here first and I'm looking to find the 3 values here, the simplest thing to do is sum of the forces in the y equaling 0, and the internal forces are fine. In your mind, you should think of this entire thing as a rigid body, and it only has this, and this force on it. It could have a weight, but I don't think he gave us a weight. So from this, I can tell you that AY is going to equal to 8, because this is the only Y force, and that's the only Y force. So I'm just going to take it off and put down here the number 8. Next thing I'm going to do is I'm going to say sum the moments about point A equaling to 0. And what I'm going to have is this distance, this, and this all together times 8. And that is going this way around A. So it is 8 times 0.75, and there's 3 individual chunks of those. So I'm just going to put it down that way. Then the only other force I've got is this. Turns out it's this far up and then that far. And it is going this way around A. Called it a tension, and it is 0.6. So for my tension, I'm just going to work this on my calculator I have here, and hopefully I get a tension of 30. Now I can immediately sum the forces, in the X. Here's what I should do. I should highlight these with different colors to indicate that each one is, because I'm sort of packing things around here. Some of the forces in the X would tend to yield that this is actually in the opposite direction and its value would be 30. So I didn't even finish writing that. So now I think he wanted to know the internal loads here on C. So you got, I guess this one's a little bit more complex because you actually have now, depending on the way, it would be more interesting if he would have put the point over on the left, or I'm going to do something interesting. I'm going to pick a more interesting point. I'm going to pick the point that sits right here. Since he has an A, B, and a C, I'll call this point D. That's more interesting to me. So if someone were to say that D is slightly above this little crevice right here, just instantly above it, what is the loads there, internal loads on D? So one of the things that you'll notice is it's a pulley, and I guess you have to assume that there's no friction here. So that means that you get a 30 here, and you get a 30 here. And now I'll go back and do the other one in a minute. Now I'm going to go back. Hang on. To the picture in the book. Hang on. And then go back over here. I'll do C in a minute, but I thought this would be more interesting. Okay, I hit control. There it is. Okay, so I'm going to zoom in on that and find my pen again, and what I've got, I got 30 here and I have 30 here. Now I've got something like this. Okay, at this particular point, since the beam is vertical, we're just going to assume a shear in a particular direction, and I'm sort of abandoning a few things here. So if I look at this, what do I get? Now, first of all, I need to know this angle. Okay. Let's see. Find my calculator here again. Oh shoot, there's no special angle here. Oh, well. So tangent of theta is equal to 0.5 over 0.75. Yes I do, I have octave up. Okay. I believe is it tangent 2? Which one is it? Hang on a second. Okay. Alright. Is there a degree component to this? I don't know if there is a degree component to this. Let's just try something. Oh, there is a degree component to it. Okay. So this is, here you can do this. Should produce something. Oh. Okay, so what you have is a function. Okay, so it says something there. Compute the or the arctangent in degrees of the corresponding elements, where you put in the actual x and the y. So my x 0.75, my y of 0.5, yeah. 56.31. So now if we want to double check that, I can find the link to this hypotenuse, and I'll do that real quick since I have .90. Now what I'm going to do, just going to list it as a h, and then I'm going to do arc cosine of in degrees of 0.75 over h. Uh-oh. I knew that didn't seem right. So I tend to think that this is more correct here. So I'm going to take this 33.69 So that was a waste of time there. Oh, yeah, it's okay. We're just going to go on and take that 33.69. So that's going to be 33.69. Now, what I'm going to do here is I'm going to sum the forces in the y equaling 0. Make this one positive. Means I have a negative n. Now, I actually have a minus 30, just the tension of this rope, times, I'm looking at the other side of it, so I'm looking at the sine of 33.69. So I get the normal equaling 2. Let's go ahead and just call that the A for angle. 30. Okay, I've already forgot 30 times sine. $16.6 roughly. The shear, sum of the forces in the x, and I've got my shear going to the right. I also have a 30 going to the right, and I have, this is the degree, I have a little bit going to the left, minus 30 cosine of 33.69. So I can move this over. And let's see, 30 times cosine of degree, whatever that angle was, minus 1 gives me minus 5.04. That makes sense. Oops. Now, because there's a little bit more going this way. Now, if I really wanted to be particular, now look at the bottom of this, and I use an x and use a y, which direction is positive, this way or this way for the shear? Well, one way to look at it is I have a normal, which usually that's written as a small n, and it's going in the negative direction, so therefore negative and then a positive, so this should be a positive. So in fact, we're going to stick with that. Now, the moment is kind of a funny thing because I'm not back at that page, but I do have, don't I have a description, or was it on the last page? It might have been on the last page, in which maybe I had that. Oh, here it is. got too much. Here, curvature, I won't get into this quite yet, but actually curvature has to do with coordinates as well, but I don't want to confuse the issue, so I'm just going to leave it as the representation there. And now I'm going to sum the moments. I'm going to consider this to be positive. I'm going to go ahead and take all this off of here. 0 is equal to. Now, the way I've drawn this is the moment sits here like that. So it's positive. Now, this component coming down at me creates the normal force that actually is going in the reverse direction. So it's actually, I should have had a minus sign in the middle of there. But it does not create a moment. However, at the very tip of this, you have this value, which is 30 cosine of 33.69 going to the left. So essentially at that upper point you have this 30 cosine of 33, and then you have 30. So the total force going to the right would be 30 minus 30 cosine of 33, or 30 1 minus cosine of that 33, which looks familiar because it sat right there. So in fact, what it is that value. And that value is going to the right at the very top. And since it's going to the right, it's basically doing this direction. So it is a minus 5.04 times its moment arm of about 0.5. Now this is cutting hairs, but I'm going to go ahead and cut a hair, and that is, this is claiming it's to right here, and I'm right here technically. But I'm going to say this is an infinitely thin beam, and D is just slightly up there. So the moment is just going to equal to about, I don't know, around 2.5. Now let's go back to C. And I'll just, now I can do things in an interesting way. One way is to take the left end, which can cause some issues, but to me, if I slice it and took the right end, my problem would be a little easier to work. But I actually could do both. I will take the right end, and so what I'm going to do, I'm essentially taking a small section. I'm going to drop down here, paste it, move it back up here a little bit. I'm basically going to copy the 30, which is this way, the 8, which is that way. Now, zoom in on this, and what I've got, okay, so this is a positive normal, this is a positive moment. Okay, again, I'm going to the left side, so the shear's got to go like this. And I guess I'll put my V down here. Now, let's double check it. So we want to double check it. We can slide back here. on the left end, it's going up, so I've got it backwards. So why is it going up? Again, X, Y. Okay, on a face like this, the normal is equal to minus I. So then the shear should be some number times J. So I stand in my own correction. Now, I guess I erased it. Okay. So now, that's pretty easy. Sum the forces in the X tells me that normal is equal to minus 30. The minus indicates compression. Okay, I'll just erase that and we'll go on from there. Now, sum of the forces in the Y, pick yourself a direction. That'll tell you that the shear is equal to minus 8, meaning it's got to flip around to offset that. Now, sum of the moments, and since I'm interested in point C, I take it about point C, and what I've got on that left end, that because these two are going in opposite directions, and then I've got this one going this way, which is actually plus 8 times 0.75. Get rid of that. And so your moment is going to be equal to a 6, value of 6. And that's, I think, it. So what I'm going to do next time is I'm going to go in here and take one of these ones that has applied moments and do a few of those. This area, for some reason, several of the videos got deleted. I'm not sure why. So I'm going to go back and add some of this content. I don't know what happened here, but everything is really slow. I'm going to have to use actually the slower computer, which I have. So I don't know what's going on here. So if you look at week 11, just for some weird reason, these 3 videos are unavailable. So I'll fill in some of this. It could be that I'll have to go back and find the link. It could be that they got closed out, meaning that they're still there, but they're made into private, because I have several videos. I have as many that are in private mode as in public mode. So we'll call it quits for right now, because I have another WebEx thing I have to go to.